So next, since we want to understand the channel, so we need to define the behavior of h of t. And the channel is time varying. So we need to look at what are the characterizations of time variations. And for that, we need to look at the correlation properties. So this function defines the received bandpass signal correlation, and this is the basic expression for correlation. And after obtaining the result, it will help us to understand what is the coherence time of these kinds of channels. So after substituting the expression of RT, which we assume that it is wide sense stationary, and what is wide sense stationary, we will see it in later lectures. So assuming this, that RT is WSS, and solving, we are left with three important expressions. So the first expression states that the correlation of R of t with itself is a function of autocorrelation of Hi of t and the cross correlation of Hq of t with Hi of t. Secondly, the correlation of H with itself depends on this autocorrelation function and the cross correlation function. And finally, the third expression, from here we can say that this phi RR of delta t is related to phi HH of delta t through carrier and real part of it. That is, we can say that this is the baseband, band pass, and this is baseband. So band pass is related to baseband through carrier and the real part of it. So we can also characterize the channel if we study the baseband. So if we can study this, we can say that we could characterize the channel. So in the end, what we need to do is we need this phi RR of delta t. So it can be easily seen from these equations, phi R of delta t can only be obtained if we have this autocorrelation function of Hi of t and cross correlation function of Hq with Hi. So next, we know phi n is uniformly distributed, and now we are saying they are independent. And why we are saying independent? Because let's say we have a transmitter and receiver. Let's say this is the phase shift across the nth path, which is phi n, or this is the phase shift across mth path, which is phi m. And both the paths are independent because they will experience different phenomena. So as a result, we will have different phase shift for this path and different phase shift for this path. So we can say these both are independent for all n is not equal to m. So now if we find out this correlation of Hi with Hi of t, this can be simply obtained by just substituting this expression Hi of t is equal to summation of n Cn cos phi n of t into the basic expression of correlation like this one in the form of H, in the form of, if we replace this R by Hi. So what we get is this is a function of expectation of theta and cos 2 pi fm max cos theta delta t. Now we have seen that this Hi of t is a function of phi n of t, but after solving this autocorrelation function, what we get is this is expectation over theta and this is a function of theta. So how we are getting this? Because when we studied this Doppler shift, we have seen that phi n of delta t is equal to 2 pi f d comma n of delta t, where this delta t can be further written as this fd comma n, which is the Doppler frequency at the nth path, can be further written as f max into cos of theta n, where theta n is the incidence angle of the nth path. So by substituting this expression into this, and finally we can replace this phi n of delta t in the form of theta n. So similarly, we can also obtain the cross correlation of HQ with HI. Now the difficulty is solving this expectation over theta. So what will help us in computing E theta is that if we consider a receiver, and we assume that the waves are coming from all the direction, that is theta n is uniform, and this model is what we know as Clark's model of 2D isotropic scattering. So because of this models, we will have the probability of theta is equal to 1 over 2 pi. So if we go on computing this expression, this autocorrelation function, and then we are getting this expression, which is a function of gain of antenna as a function as a function of theta, which is usually considered to be 1 when it is uniform, and p of theta, which we said it is 1 over 2 pi. Then on solving this integral, what we are left with, this expression where J naught is the 0th order Bessel function of first kind. So computing this autocorrelation function will help us obtaining the expression for phi h of delta t, and then using phi h of delta t, we can find phi r of delta t, which we require to understand what is the coherence time of this channel. Now we want to look at this autocorrelation function, the plot for this autocorrelation function, which is represented by phi hi is equal to J naught 2 pi fm delta t. So this is what we have autocorrelation, and we will try to understand this Bessel function. So in the x-axis we vary fm into delta t, and in the y-axis we will see this value autocorrelation function normalized by omega p by 2. And there are two important things to note here. First, the maximum gain that can be achieved is 1, and secondly, this autocorrelation function approaches 0 at a certain value. And this is very important because here we will define the coherence time, which means that during which the signal is correlated to